Thank you, Joe. I thought that this talk would kind of set the stage for this meeting because, of course, CMOS is kind of the default technology, right? It's the technology to beat. And so it's good to be aware of where CMOS is going and where we think the limits of it are. And then I'll also talk about some techniques for potentially extending the life of CMOS, although they're quite challenging. And I'll present some results that were generated by Alex Edwards, who is a student in Joe's group, and he's overseas right now, so he couldn't be here, but some of the results in here are from him. There's a bunch of other people who have helped with our research program at Sandia over the years, and a particular person that contributed to this talk was Brian Tierney in the Rad Hard CMOS group, and of course Joe and Alex are a big help. So just a brief overview. The first part of the talk is going to talk about the limits of CMOS, and I'm going to argue that basically, we're only about at most around 10x away from ultimate limits on the low-level energy efficiency of conventional CMOS, and that's, I think, closer than a lot of people realize. And but there are potential ways to extend the life of CMOS. Something I call fully adiabatic switching, as opposed to sort of quasi-adiabatic techniques that some people use. And the focus of the work that I did with Alex last year was basically analyze how much we can increase throughput density by increasing the energy efficiency of CMOS through adiabatic switching. And, we found quite nice results there for low-level energy efficiency, but there's some caveats to that. All right, so let me just dive in. Just for context, here are a couple of Department of Energy supercomputing systems that have been built over the years. In 1997, we had the ASCII Red system, which was about a teraflop. 2022, Frontier is about an exaflop, so there's about a factor of 1,000,000 increase of performance, raw floating point ops per second. But the power requirement only increased 25x, which means that the energy efficiency of computing in those systems increased by a factor of 40,000 over that 25 years. And if you look at where that comes from, there's about a factor of 200 reduction in gate energy per transistor. And so that means the remaining factor of 200 was from higher level optimizations, architectural improvements, and so forth, and software improvements. So that's kind of interesting that it factors like that. And notice that per decade, there's been about a factor of 8 increase in both of those efficiency figures, every 10 years on average. So it turns out we've only got about one more of these factors of 8 left at the device level. And I'm not sure exactly how much there is at the architectural level, but it might be similar if you imagine that we generally improve whatever is easiest to improve next. So maybe these things improve roughly in concert, and maybe we'll run out of steam at around the same time too, but that's a little speculative. Of course, the rate of performance improvement has not been completely uniform over this period. There was this knee in 2013 where the slope on this log chart suddenly changed from, this is the aggregate performance of the top 500. It went from improving at 85% a year to improving at only 40% a year. So that's interesting. So it's not irrevocable that things keep improving at the same rate. In fact, I'm going to argue there's going to be another downturn here soon. So looking forwards, we can consult the International Roadmap for Devices and Systems to get some forward-looking prospects. And I'm involved with the editing of this on the Beyond CMOS chapter and a little bit on the cryogenic electronics and quantum computing chapter. But what I'm going to talk about today draws from the more and more chapter, which is basically future of conventional CMOS lithography and design. And I'm going to go into more detail on part of this later, but for now, I just wanted you to see what the device architectures look like looking forwards. So we have FinFETs in the latest generation. We're going to nanosheets starting around the 2025 node. And then there's various things like complementary FETs and multi-tier logic that are in the roadmap looking forward over the next 10 or 15 years. So big picture, the end of energy efficiency improvements in conventional CMOS is very near. And if you look at the roadmap data, there's only about a factor of 2 improvement in the energy per typical logic node at nominal voltage levels. You can do things like lowering the voltage, which I'm going to talk about. But the issue here is that the reason you can't get a whole lot lower is that if you look at the energy per nanosheet channel, it is actually getting down here to the several tens of KT level. And that's the level where we expect thermal noise to start to become a problem. You get fluctuations in the channel potential, and it's going to impair the device function on short time scales. So it's believed that we're not going to be able to get much farther than, around the neighborhood of a few tens of KT. And that's not far below where we're going to be at the end of the roadmap. And the total energy per logic node is a lot larger than this because there's various overheads that come into play. You got several nanosheets per transistor, 2 transistors per inverter or per logic signal driving a downstream gate. And you've got a bunch of other overhead factors here, like for parasitic capacitances, fan out in logic, and sizing of devices. So interestingly, maybe we've got about a factor of 8 here between the factor of 2 here and the factor of 4 here. But if you look at the comparison between where we are now and the human brain, you find there's only about a factor of 8 difference in energy dissipation per floating point operation, if we can pretend that a synapse firing is doing a floating point operation, like it's adding the weight of that synapse into the activation of the downstream neuron. That's a very rough comparison, and the brain, of course, is doing more than just firing synapses. But, if you amortize the total power dissipation of the brain over the number of synaptic firing events based on this rough estimate, that's what you get. So maybe that's just a coincidence that it turns out that way, or maybe not, since we aren't actually beyond brain efficiency yet in commercial systems. It's hard to say for sure, but I'm going to talk about some ways that we can possibly get beyond that level of efficiency. First, let me just say a little bit about where this limit of CMOS comes from. Back in the 19th century, this phenomenon of thermal noise was discovered, or thermal fluctuations. And, it took a while to understand what was going on there, but the basic story comes down to Boltzmann, who showed that essentially any possible physical system that's in thermal contact with an environment will experience fluctuations in its energy given by the Boltzmann distribution, which is this exponential distribution. So, the larger the energy difference you're talking about, the lower probability the fluctuation is going to be. But there's always still some chance of having an energy different from the equilibrium level. And so this ends up affecting the physics of transistors, because in a field effect transistor, you've got a potential energy barrier. And when the transistor is off, you're not supposed to have electrons leaking over that barrier, but there's always some probability that thermal fluctuations will lift an electron up onto that potential energy surface, at which point, if there's like a small voltage between source and drain, it can drift across the device and you get some current. And so the current in this sub-threshold region, when the device is nominally off, scales exactly according to the Boltzmann distribution, exponentially with the applied gate voltage, which tends to suppress the height of the potential energy barrier. And so as a result of that, you can calculate that, for a given ratio between on current and off current that you want to achieve, you have to have at least a certain amount of energy difference in the potential in the channel between the on and off states of the device. And, assuming that a minimum device is going to have at least one electron that you have to move to change that potential or to carry a current through the device, you conclude that the energy has to be at least kT times natural log of the on-off ratio. And if you look at the on-off ratios specified in the roadmap in, say, the year 2028, that tells you you're going to have at least 30 kT to achieve that on-off ratio per electron channel, essentially. So that's where that comes from. And then energy efficiency ends up limiting throughput density, because even today the aggregate computational throughput per unit area in CMOS is primarily limited by power dissipation constraints. People with gaming systems might know you can overclock your GPU more if you cool it down more, and so forth. So on the roadmap, they have this factor 2 improvement in energy efficiency and a factor of about 15 improvement in throughput per unit area if you were not constrained by energy efficiency, but you are. And so, the roadmap observes that if you want to, with the efficiency only improving 2x, if you improve the throughput per area by about 15x, you get about an 8x increase in power dissipation density. It was not exactly half of this because there's some more architectural things that change a little bit. But so if you have a GPU that's dissipating almost 1,000 watts today, as some of the high-end ones do, then now you're going to have many thousands of watts at the end of the roadmap if you really increase the throughput density that much. And it's possible to do this because we're still increasing device density through multi-tiered logic and things like that, and decrease cell sizes. But if you wanted to keep the power dissipation the same, or power per unit area, and you continue scaling, that means you're going to have to slow your clock speeds down. So a CPU that's, say, 3 gigahertz today would have to be slowed down to not exceed that power dissipation constraint to like only a few hundred megahertz, right? So you don't gain much throughput. You only gain throughput in proportion of the increase in energy efficiency, okay? So this is a motivation to start looking really seriously at energy efficiency. So now let me talk about adiabatic switching. A simple way to think about what's happening in adiabatic switching is you're charging the capacitances in the circuit with effectively a constant current source instead of a constant voltage source. And when you do that, you decrease the energy that's dissipated. It's basically improved by this factor of RC over T. So if you transition slower than the RC time constant of that charging path, then you'll dissipate less energy in switching the state of that capacitance. And in practice, we use a voltage ramp to sort of approximate a constant current source, and that works fine. And in principle, we can make the energy dissipation as small as we want, modulo whatever leakage there is for the off-state devices. And if we really want to get aggressive at this, we can adjust the device architecture to reduce leakage. Here's just a couple of examples of circuit styles that adhere to this principle of fully adiabatic switching. This is an old one whose roots go back to the early 90s that I call two-level adiabatic logic. This is a structure of a shift register, can be generalized to an arbitrary logic pipeline. And it has this sort of mirror image structure with complementary forwards and reverse paths relating to the reversibility. It has several of these clocks that have these voltage ramps that are driving the adiabatic transitions. And there's another variation of it that's fully static as well, which has some advantages, like, you can slow down the clocks or pause them while you're debugging or while you're waiting for information, and it still works. So there's a lot more on this. If you're interested, you can read the papers, but I don't have time to go into detail. But here's one result from some simulations we did recently at Sandia. This is in a couple of different technology nodes that we manufacture internally at Sandia. And you can see in one of these cases, we can make the energy dissipation per transition, per transistor, as small as 2 attojoules. And notice this is over 14,000 times less dissipation than a synapse firing in the brain on average. So if you could simulate a synapse firing with 14,000 of these operations, then you would have something that's as energy efficient as the brain. And maybe you can do even a little more work than that. So that's kind of interesting. That sort of motivates us to keep pushing on this idea. And so that leads to the work that Alex did last summer. So our approach here is just to sort of maximize the throughput density for both adiabatic and conventional switching in CMOS. And this is raw throughput density, just, logic switching events per second per unit area. And it's just a straightforward optimization. Given the power density constraint, we consider various voltages. We make sure that the leakage power does not exceed a constraint. We don't want it to be more than a certain percentage of total power dissipation. So we reduce the device density if necessary to achieve that, and then select a switching frequency where we meet the power density constraint. And it's chosen differently for adiabatic and conventional technologies because the power scales with frequency differently. And then you just plot the results. So let me quickly go through the results. For standard voltage conventional switching, of course, as expected, the throughput scales down proportionally as the power dissipation constraint goes down. Also, at some point, you can no longer pack in devices at the maximum density because just the leakage will use too much power. And so you can decrease the device density. That doesn't affect the throughput of conventional CMOS because, it's already completely limited by energy efficiency, which is not improving as you slow it down. And so, you just have that the gate densities starts decreasing, but then, you can maintain a constant frequency below that point. And you're just limited by the throughput, by the power density constraint. So then you can try optimizing the operating voltage for conventional logic. And when you do this, you find that the optimal voltage starts out like around the threshold voltage and decreases as the power density constraint becomes more stringent and levels off at about half of the threshold voltage. And as a result, you gain more energy efficiency due to these lower voltages. Leakage improves as well because lower voltage means less V squared over R power, right? And so you're able to maintain a higher density of devices and actually improve the throughput. And so I believe this is the main strategy industry is going to use looking forwards once they run out of scaling, the end of scaling. So a lot of improvements over the next 15 years in practice will probably come from this low voltage operation techniques. So, when you're trying to pack in devices at the maximum density, you can actually achieve higher frequencies at lower voltage due to the greater energy efficiency. And here's what happens if you consider adiabatic switching. And here we're just using the standard VDD levels. We're not even considering low voltage yet. And you can see that the slope of improvement is better as you reduce the power density per die. And that's because of the adiabatic scaling, the fact that the energy dissipation per operation scales down as you stretch out the time for those voltage ramps. And so you end up doing like 21 times better than even voltage optimized conventional CMOS at low power levels per die. And these low levels per die are relevant if you think about stacking up many die within a package to try to improve throughput at the package level. So that's interesting. But then we can also optimize the voltage as well and switch adiabatically. And interestingly, when you do this, you find the optimal voltages are around threshold, which, it turns out that's better because you don't have to lower the energy per nanosheet as much, and you'll probably avoid these thermal noise problems that I was talking about. And so here you find there's about 100x potential improvement in energy efficiency by the end of, or by, I guess this was by 2028 at the low end of the scale here. So overall, in terms of energy efficiency, these are the best case points from the previous graph. As I said, the conventional dissipation is only improving by a factor of 2 at nominal voltages. If you aggressively lower the voltage to subthreshold, you can maybe get this additional factor of about 25, and so 50x improvement overall. But here you're probably getting down into deep in the thermal noise danger zone because the energy per nanosheet is only about 6 kTs. And so this may not actually work. If you are a little more conservative and you only lower the voltages to about threshold, you get about a factor of 6 here. So 2 times 6 is about 12x total improvement. With adiabatic switching, conceivably you could get as much as another factor of 13 beyond this point. And so altogether that's 640, and that's at standard voltages. And if you lower voltages to around threshold, you get another factor of 8, altogether about a factor of 5,000 improvement in energy efficiency. But I should mention this is not realistic because this is, again, the low-level dissipation, and there's a lot of overheads to designing adiabatic circuits. You have to use reversible logic. And so in practice, you're not going to get this whole factor of 5,000. You'll get something less depending on how much overhead you have in your logic design. And so that's, a question for further research to figure out exactly how well you can do for standard functional units like, adders, multipliers, and so forth. So in conclusion, we have these really fundamental limits from thermal noise that are going to limit what we can do with CMOS. And those of you working on alternative technologies should keep in mind that any physical system still has thermal noise. And so you have to have a strategy for how to deal with that in your logic scheme. It's not clear to me yet, personally, if any competitor to CMOS can possibly get far beyond this, as long as it's still a digital technology. Maybe some of the analog approaches can do better. But, this is going to be a fundamental limit for, I think, any digital technology. Adiabatic switching gives you a potential workaround where if you compare at the same voltages at the end of the roadmap, we maybe get about to a factor of 400 improvement in energy efficiency. And that's with standard leakage levels. If you adjust the devices to lower leakage, we can maybe get further. And there's lots of work to do to further refine this study. This is just a preliminary study, not yet ready to publish, but hopefully we'll get a journal article out within the next year. Yeah. That's it. Sorry if I went over.